This situation described presents a potential overload scenario for the 300 kV amps, 208Y/120Y volt, three-phase pipe-mounted transformer. While the primary fuse of 45 amps offers protection on the primary side, the secondary fuse is rated at 1200 amps and 800 amps, respectively, primarily safeguard downstream equipment rather than the transformer itself. The core issue is the combined potential load in the secondaries, which could surpass the transformer's rated capacity of 833 amps. If the load connected to the 1200 amp secondary remains below 833 amps, the transformer will likely operate within safe limits. However, if the load in the 1200 amp secondary exceeds 833 amps, the transformer faces a high risk of overloading and potential failure. The 800 amp fuse on the other secondary will not activate until its load surpasses 800 amps, a level dangerously close to the transformer's maximum rating, offering inadequate protection against overloads on the 1200 amp circuit. To mitigate this risk, several measures can be taken. Firstly, reducing the load on the 1200 amp secondary to a level below 833 amps is essential. Secondly, installing a fuse or circuit breaker rated at or below 833 amps on the 1200 amp secondary will provide direct overload protection for the transformer. This protective device will trip before the transformer is subjected to excessive current draw. Thirdly, replacing the existing transformer with a larger unit capable of handling the combined load of both secondaries, at least 2000 amps in this case, is a definitive solution. A qualified electrician or electrical engineer should assess the facility's actual load requirements. Here's a more detailed explanation of the concepts involved. A transformer works by transferring electrical energy from one circuit to another through electromagnetic induction. It has a primary winding connected to the source voltage and a secondary winding connected to the load. The transformer's kilovolt amps rating represents its apparent power capacity, which is the product of voltage and current. In this case, a 300 kV amps transformer can supply a maximum of 833 amps at 208 volts or 120 volts on its secondary side, calculated using the formula kilovolt amps times 1000 divided by the voltage, and then divided by the square root of 3 for three-phase systems. Fuses and circuit breakers are overcurrent protection devices designed to interrupt the flow of electricity when the current exceeds a predetermined level. They protect equipment and wiring from damage caused by overloads and short circuits. Fuses are one-time use devices that melt and break the circuit when the current exceeds the rating. Circuit breakers are reusable devices that trip and interrupt the circuit and can be reset after the fault is cleared. Overloads occur when the current flowing through a circuit exceeds its rated capacity. This can be caused by excessive loads connected to the circuit or by a fault in the equipment. Overloads can cause equipment to overheat, which can lead to damage, fire, or even explosion. Short circuits occur when there is a direct connection between 2 points in a circuit that have different potentials. This can be caused by damaged insulation, faulty wiring, or accidental contact with conductive materials. Short circuits cause a very high current to flow, which can quickly damage equipment and wiring. In this scenario, the primary fuse is sized to protect the transformer from overloads on the primary side. The secondary fuses are sized to protect the downstream equipment from overloads on the secondary side. However, the secondary fuses do not necessarily protect the transformer itself. If the total load in the secondaries exceeds the transformer's rating, a transformer will be overloaded, even if the individual secondary circuits are protected by fuses. This is because the transformer is the source of power for both secondaries, and it must be able to supply the total current demanded by both loads. If the transformer is overloaded, it will overheat and could eventually fail. It is crucial to ensure that the transformer is protected from overloads, even if the individual secondary circuits are protected. This can be done by installing a fuse or circuit breaker on the secondary side of the transformer that is sized to protect the transformer itself. The size of the fuse or circuit breaker should be based on the transformer's kilovolt amps rating and the secondary voltage. It is also important to consider the inrush current of the loads connected to the secondaries. Inrush current is the momentary surge of current that occurs when equipment is first turned on. Some equipment, such as motors and transformers, can have very high inrush currents. The fuse or circuit breaker must be able to withstand the inrush current without tripping. The National Electrical Code, NEC, provides guidelines for sizing overcurrent protection devices. NEC Table 450. 3 indicates the proper overcurrent protection for transformers. The primary side protection should not exceed 125% of the transformer's primary current rating when using a circuit breaker, or 300% when using a fuse. The secondary side protection should not exceed 125% of the transformer's secondary current rating. These are maximum values, and smaller fuses or circuit breakers may be used to provide better protection. In addition to overcurrent protection, transformers should also be protected from other hazards, such as voltage surges and lightning strikes. Voltage surges can be caused by switching operations, lightning strikes, or other disturbances in the power system. Surge protection devices, SPDs, can be installed to protect transformers from voltage surges. Lightning arresters are also used to protect transformers from lightning strikes. Regular maintenance and inspection of transformers are essential to ensure this safe and reliable operation. Transformers should be inspected regularly for signs of damage, such as cracks, leaks, or corrosion. The connections should be checked to ensure that they are tight and secure. The oil level should be checked to ensure that it is within the proper range. Transformers should also be tested periodically to ensure that they are operating properly. These tests can include insulation resistance tests, turns ratio tests, and impedance tests. The results of these tests can be used to identify potential problems before they lead to failure. When selecting a transformer, it is important to consider the load requirements, the voltage levels, and the environmental conditions. The transformer should be sized to handle the maximum load that will be connected to it. The voltage level should be compatible with the source voltage and the load voltage. The transformer should be suitable for the environmental conditions in which it will be installed. For example, if the transformer will be installed in a damp location, it should be designed to withstand moisture. In summary, the transformer's current configuration poses a potential overload risk due to the combined capacity of the secondary fuses exceeding the transformer's rated amperage. Mitigation strategies involve reducing the load on the 1200 amp secondary, installing appropriately sized fuses, or upgrading to a larger transformer. Consulting with a qualified electrician or electrical engineer is crucial to implement the correct safeguards and prevent transformer failure.